Today we discuss how constraints reduce the degrees of freedom of a system. Here we see a simple pendulum. For the simple pendulum, we know we have a bow here. It is the string attached to bow that is making an angle theta with respect to the vertical. Okay, this is the fixed end to that end. The bow of the pendulum is attached through a string. It is making an angle theta with respect to vertical. If we consider bow as a particle, it initially, if it is not attached to the fixed point O, if it is free, it has 3 degrees of freedom because it has coordinates x, y, z. It can move freely in x, y, z direction, and we say it has got 3 degrees of freedom. Independent variation of x, y, z are possible, and we say it has got 3 degrees of freedom. Now you attach a string to the particle, to the bob, and allow it to oscillate in just a plane. Okay, you make it oscillate in just a plane. Then constraints are there. What are the constraints? Since it is oscillating in a plane, we can say there is a constraint z equal to 0. Okay, the oscillation takes place in xy plane, so we can say z is a constant or z equal to 0. So this is one constraint. Then there is x square plus y square equal to L square, where L is the length. Okay, x square plus y square equal to L square. So this is the second constraint. Okay, x square plus y square, this is the coordinates are x, y, and this is x, this is y. So x square plus y square is equal to L square. So the second constraint. So how many constraints? 2 constraints. So what happens is the bow or the particle, it originally had 3 degrees of freedom. Now due to these constraints, z equal to 0, x square plus y square equal to L square, when it becomes a simple pendulum oscillating in a plane, 2 constraints are there, and 2 constraints reduce the degrees of freedom. So 3 minus 2, so that is equal to 1. So the degrees of freedom, DOF, this is DOF, the degrees of freedom, that now becomes 1. Okay, so we say the system has 1 degree of freedom. So we need just one independent variable to describe the system because the degree of freedom is now 1. And we are choosing that, we properly choose that coordinate, and that we choose as theta, this angle theta, the angle made by the string with respect to the vertical, that is taken as the coordinate, and it is called generalized coordinate. Okay, this is the generalized coordinate. When you are using this coordinate, you need not consider the constraints. Okay, so it has one generalized coordinate, theta. Okay, and we represent q, generalized coordinates are represented by q, so q equal to theta. And what are the transformation equations connecting the old coordinates x, y, and the generalized coordinate theta? We know here x is what? If this is L, x is L sine theta. Okay, this is L sine theta, and this is L cos theta. Okay, so the transformation relations are x equal to L sine theta and y equal to L cos theta. Okay, these are the transformation relation. And if I take a double pendulum, okay, double pendulum, this is an interesting example. Here we have two particles, two bobs, okay, two bobs. This is this bob, this is attached to fixed end. Another bob is attached to the to this bob. Coordinates of the first one are x1, y1, z1. Second one are x2, y2, z2. And since they are oscillating in a plane, we can say the constraint equations are z1 equal to 0 for the first bob, for the first particle, for this particle z1 equal to 0, for the second particle z2 equal to 0. The coordinates of this particle is x2, y2, z2. Okay, and what about the other relations? X1 square plus y1 square equal to L1 square, because this is the length of this pendulum. So x1 square plus y1 square equal to L1 square, and about L2, x2 minus x1 square plus y2 minus y1 square equal to L2 square. Okay, x2 minus x1 square plus y2 minus y1 square equal to L2 square. So in that way, there are four constraint relations, constraint equations. Since we had two particles, or we have two particles here, it had 6 degrees of freedom. Okay, 3 into 2. Each particle has 3 degrees of freedom, and there are two particles, so 6 degrees of freedom are there. And there are four constraint equations. So what happens? 6 minus 4 equal to 2 degrees of the degrees of freedom now decreases to 2. Okay, so d of is equal to 2. So we appropriately choose the generalized coordinate. We need two generalized coordinates. So q1, q2, q1 we are choosing as theta 1, and q2 we are choosing as theta 2. Okay, so the theta 1 and theta 2 completely describe the system. Okay, 2 degrees of freedom, and we are choosing theta 1 and theta 2 as the generalized coordinates. Okay, now what about the transformation relations? As we wrote in the first case, transformation relations now becomes x1 equal to L1 sin theta 1, that we know, y1 equal to L1 cos theta 1. And what about x2? x2 is L1 sin theta 1 plus L2 sin theta 2. Okay, so x2 is the distance from this point to this point. Okay, this is L1 sin theta 1, and this part is L2 sin theta 2. So when you add them together, we have L1 plus L1 sin theta 1 plus L2 sin theta 2, and y2 is L1 cos theta 1 plus L2 cos theta 2. So these are the transformation relations. So we can write x1 as a function of theta 1 here, and x2 can be written as a function of what? Theta 1 and theta 2. Similarly, y1 is a function of theta 1, but y2 is a function of theta 1 and theta 2. Okay, generally we can write xi or yi or zi. This can be written as functions of t, yi can be written as functions of q1, q2, q2t, zi can be written as functions of q1, q2t. Okay, xi, yi, zi, that can be written as functions of the generalized coordinate. So generally, for any system, the coordinates of the ith particle xi, yi and zi are the coordinates of the ith particle. that can be written as a function of the generalized coordinates. And in some cases time also may be there. Okay, and we can write Ri. Ri is the position vector corresponding to the ith particle. It can be written as function of q1, q2, q3, etc., comma time. Okay, so Ri is a function. Ri, what is Ri? The position vector of the ith particle. There are many particles in the system. That can be written as the function of the generalized coordinate. So these are the transformation relations.